as the processes, disease processes, inflammation, cell injury, and of course, cancer. Now you have seen this relationship, and the different disciplines of medicine that are dependent on biochemical reactions and processes. Okay, do you have this in your in your laptops? Now this tells you now that this is a two-way street, connects biochemistry and medicine. Now you have that green line. On top, you have what you call this on top you have nucleic acids, proteins, lipids, carbohydrates that are present in your body.
Glow eh. Tubungan ni Glow.
And down below are the disorders. No? Genetic diseases, sickle cell anemia. This is because of a problem with the protein here. So that means that the protein or your globin in your hemoglobin is not well synthesized. So there's something wrong with the genetic code in that particular gene. Okay. Now, problems with lipids gives you very good example, atherosclerosis. However, this atherosclerosis has also a genetic component. It has a genetic component. And likewise, problems with carbohydrates, you come up with diabetes mellitus. The problem in carbohydrates for your diabetes mellitus got to do with insulin, the hormone that regulates your carbohydrate metabolism. So without insulin, the sugar cannot get into the cell and cannot be utilized. So this is just to show you that biochemistry and medicine goes hand in hand. Okay? All right, biochemical processes underlie human health. Biochemical research impacts nutrition and preventive medicine. The definition of health by the World Health Organization says complete physical, mental, social well-being, and not merely the absence of disease or infirmity. So the maintenance of health requires optimal dietary intake of vitamins, amino acids, essential fatty acids, minerals, and water. You know, of course, what vitamins are, what amino acids are, essential fatty acids. You must have heard, of course, of omega-3, omega-6, omega-9 fatty acids. And then, of course, minerals. Foremost mineral that you can always remember in your body is calcium. That's in the bones. But actually, your calcium is not only in the bones, but it also are found in the neuromuscular processes. Minerals, now especially during this time in pandemic, most important mineral would be zinc. Why zinc? Because zinc boost your immune system. And that's what we are having right now. That's only our only weapon. There is no medicine for COVID-19. There is no vaccine yet. So what we have to do is to strengthen our immune system. And as I've said, zinc is very, very important in boosting the immune system. That's why the pharmaceuticals now are producing supplements that contain zinc. And another mineral that is important for also for your immune system is selenium. No? And then of course water. Water is very, very important. Okay? So most diseases have biochemical basis. Aside from the organisms, environmental pollutants, many diseases are manifestations in the genes. So we could call them genetic diseases. No? Diseases due to inability of the protein that is used in your body, or the protein that forms part of the chemical processes are not well synthesized. Now, chemical reactions or biochemical processes, each of which can adversely affect one or more critical biochemical function. I've seen here a spelling of the biochemical and adversely. Okay. So major causes of diseases. We have physical agents, chemical agents, including drugs, whether those drugs are legal or illegal. And you have biologic agents, oxygen lack, genetic disorders, immunologic reactions, natural nutritional imbalances, and we have endocrine imbalances. Okay, physical agents, of course, trauma, extremes of temperature, sudden changes in atmospheric pressure. Can you give an example of changes in atmospheric pressure?
Diving, Doc.
Okay.
Diving. Scuba diving.
We call that barotrauma. No? Trauma because of changes in barometric pressures. Okay? And we call them, the trivial name is the bends. No? Okay, so radiation. Now, there are so many forms of radiation. X-ray, UV rays, these are all radiation. And radiations from coming from your laptop, coming from your cell phones. No? These are your frequencies. And there are so many who are opposing now the putting up of this 5G. At present, we are using 4G in our digital devices. Okay? And then we have electric shock, of course, electricity, chemical agents, okay, toxic compounds, therapeutic drugs, and also those illegal drugs. No? Biologic agents. Oh, number one here is viruses. The one that we are having now, the coronavirus. Then bacteria, fungi, higher forms of parasites, including human parasites. Oxygen lack, loss of blood supply, depletion of oxygen carrying capacity. Oxygen carrying capacity, that means you are referring to hemoglobin. Hemoglobin is not able to carry the oxygen. Perhaps the iron there is in the ferric state so that oxygen cannot be carried. And poisoning of oxidative enzymes. So usually the free radicals. Genetic disorders, of course, congenital or molecular. Then you have immunologic reactions. Allergy is an immunologic reaction. Now this one is anaphylaxis or anaphylactic shock. This is one thing that you should avoid when you are already practicing. Your patient come into your office in a vertical position, and then you do something, especially when you inject antibiotics, and the patient comes out in a horizontal position. Okay? Autoimmune diseases. Now, our immune bodies are probably are overactive, and it destroys your normal tissues. Now, this is autoimmune diseases. Nutritional imbalances, of course, you have seen this. Deficiency not only of proteins, carbohydrates, vitamins, minerals, but deficiency due to lack of energy. No? That's energy deficient. Then you have endocrine imbalances, most common with your endocrine imbalances, you have your diabetes mellitus. Okay. Let's go to this one. Biologic investigations and laboratory tests that is being used. So on one column you have use, on the other column there on the right are example. So to reveal the fundamental cause and mechanism of the disease, example is the demonstration of the genetic defect in cystic fibrosis. Okay. Number two, a rational treatment of the disease based on the item above. So if you know what is wrong, let us say that the patient cannot tolerate phenylalanine. Phenylalanine is an amino acid. An amino acid, and this amino acid is part and parcel of the protein that you are eating. So this is quite a problematic because you need protein. No? You need protein. And most protein contains phenylalanine. So your diet I'm sorry. So your diet must be free of phenylalanine. Otherwise, you will have a condition known as sorry, thank you. So you must have a diet low or free of phenylalanine if you have phenylketonuria. Number 3, to assist in the diagnosis of specific diseases. The use of plasma levels of troponin I or T in the diagnosis of myocardial infarction. Now, you will meet this troponin in the skeletal muscle as well as cardiac muscles. To act as a screening test for early diagnosis of certain diseases. So, we have a measurement of blood thyroxine or thyroid stimulating hormone, TSH, in the diagnosis of neonatal congenital hypothyroidism. Okay, the next one is to assist in monitoring the progress or worsening or remission of a certain disease. So we do enzyme assay of certain enzymes, which is, my God, which is unique to the disease. So we have here the enzyme ALT or alanine transaminase, and monitoring the progress of infectious hepatitis. To assist in assessing the response of disease to therapy, use of measurement of blood carcinoembryonic antigen or CEA in certain patients who have been treated for cancer of the colon. Okay, so use an example. All right. Yes, you have question? Yes, Katrina? What's the question? All right, let's continue. Are you familiar with this Human Genome Project or the HGP? This Human Genome Project is a race of research companies to be able to sequence the human DNA. So it's called Human Genome Project. Now, there are two prominent countries involved in this. This is France and United States. In France, they are all privately owned, while in the United States, one company is government owned and the other is a privately owned. Now, whoever is the one to finish the sequencing of the genome, human genome, he has the right to patent it. So if one company is able to finish it and just patent it, all of the researches done on the DNA could not proceed unless they have the permission of that particular company who sequenced the genome. So this race in the sequencing started in the late 1900s. And in the mid-2000, there was a news that a company have sequenced the human genome 90% already. So just only 10% more. Then in 2003, the company that is owned by a private person in the United States, and this company is headed by Venter. So they were able to finish the sequencing of the human genome, and they were afraid that Venter might patent the procedure or everything about the DNA sequencing. However, Venter has a love for humanity, and so he did not patent it. So anybody can do its work without the permission from Venter. No? You know, if Venter will ask for payment for every time if you ask for his permission, no, he could be a very, very rich man. But he did not patent it. He said it belongs to humanity. So there are still people like that, no? Unlike the people that we have around who are greedy. Okay, so they finished that in 2003, just 50 years when Watson and Crick, you know who they are, no? They were the first to describe the double helical structure of the DNA. All right, so the implication of this accomplishment, medicine and all biology are benefited, and the benefit is unlimited. Now they are even tinkering now into replacement therapy. And the replacement that they are now going into is gene therapy. So gene therapy. So if you have a defective gene, the idea is to remove that gene and put a gene that is healthy. Although this is done in lower animals, and there was no report yet whether they are successful. But eventually, there will be some results. Huh? Okay. So, if you want to be forever young, no? They will just increase the telomerase in your gene so that the cells can regenerate. So old cells are removed and then new cells are being used as replacement. But that is several years from now. I don't know if we'll be still around when they can do that. Okay? Now, as a result of this Human Genome Project accomplishment, new fields of science and medicine are formed, or it just spring out. So we call them omics. So we have glycomics, proteomics, lipidomics. So as you can see, all of those disciplines now come from this HGP genomica. Okay. Now, biochemistry is not listed here because biochemistry predates the commencement of the HGP, meaning the biochemistry is the mother of HGP. Okay? Oh, water and pH na. By the way, that's the end of the chapter, chapter 1. Then, to aid you in your study, you go to the summary. And if you look at the summary, it mentions the salient points that are found in the chapter. Now, biochemistry is not really very hard, as a lot say that it is very hard. It's not. Just try to fall in love with biochemistry and you will find it easy. No? Now, during this crisis that we have, you do not have so much activity but to stay at home, and all you have to do is just read. No? All you have to do is just read. And that's what you are being asked to do. Read, read, and read. Okay? Let's continue. Water and pH. Water is very, very important. We mentioned that yesterday. I was coughing and water relieved me with the cough that I have. Okay, importance again. Now, biomedical importance of water. First, because you consider ability to solvate, meaning to dissolve a wide range of organic and inorganic molecules derived from the ability of water to do this because of the dipolar structure. What do you mean by dipolar? When you say dipolar molecule, a molecule that has two charges, a positive charge and a negative charge. There you are. Your water, forms dipoles. This is the tetra. That's the tetrahedral structure of your water. You have hydrogen here, you have another hydrogen here, and this is all attached to your oxygen. Okay? Now your hydrogen is positively charged there. So this area is positive. And that area there is negative. You know what's a tetrahedron? What structure comes to your mind when you say tetrahedron?
Pyramid po.
A very good example is the pyramid of Egypt. That's a tetrahedron. But the tetrahedron of water is skewed, meaning it does not have the same length of the bases. The base of the tetrahedron, they do not have the same length. As you can see it here, oh. I have a long base here, a longer one, short, and longer. And this is the shortest portion of the base. Now imagine this, that this is the base, and what you have here is the apex. Okay? Now if this was the pyramid of Egypt, this one should equal that one, no? And also equal that one there. This should also equal that one. Okay. So as a result of this, you have a positive side and you have a negative side where you have your electrons. And here are your protons here. Okay? So a molecule with electrical charges distributed asymmetrically about its structure is referred to as a dipole. Water's strong dipole is responsible for its high dielectric constant. Never mind that. Don't bother yourself what is the dielectric constant. Okay? I will not ask you how many coulombs is the water. Okay. Wait a minute. Water forms hydrogen bonds. Is one of the important function of your water. It can easily form hydrogen bonds. Okay? A hydrogen bond. So I'll give you an example. There you are. So this water, this oxygen here is shared by this hydrogen with this hydrogen on the other molecule. This is a water molecule. This is also a water molecule. And this is negatively charged, and this is positively charged. So they form a bond. But the bond is a weak bond. That's why it is dotted. It is not like this bond here. No, it's quite a strong bond. And also this one. All right, so you have one water there, another water. Now here you have several water molecules. One water molecule, another water molecule, another water. And these are hydrogen bonds. These dotted lines. Okay? Because of that, it has the power to solvate, meaning dissolve, no? Other molecules. Okay. Water molecules form hydrogen bonds with other molecules. Now, what is this molecule here? Huh? This is your favorite. Ethanol, right? Ethyl alcohol, the drinkable alcohol. Huh? And this is water. See? Oxygen is being shared by this hydrogen here, right? Now this one. You have another ethyl alcohol here, and another ethyl alcohol. And so, form this hydrogen bond. And then we have here a nitrogenous compound with a hydrogen. And then we have here with two radicals and an alkene. Oh, this is an alkene. You have double bond. Okay. So still you can form hydrogen bonds. Oh. So what do you mean by polar groups? What do you mean by polar groups? And the opposite of that is non-polar. Diba? Okay, your polar groups. No, and the non-polar. Okay. Interaction with water influences the structure of biomolecules. Now we have covalent and non-covalent bonds, which stabilizes your biologic molecules. The hydrogen bond that you have seen is a non-covalent bond. Non-covalent bond. Non-covalent bonds are weak bonds and can be easily broken, while your covalent bonds are strong bonds. Examples of these bonds are glycosidic linkage or glycosidic bond. You have your peptide bond, you have ester bonds. Now, non-covalent bonds. One, we have seen this already, and that is your hydrogen bond. There are still others. There are still other bonds. Covalent bond is the strongest force that holds molecules together. Non-covalent bonds have lesser magnitude. So, covalent bonds are hard to break, and non-covalent bonds are easy to break. Why do you need to break these bonds? Now, for example, in the process of digestion, the bonding there of the peptides of the amino acids would require, of course, the energy to break the bond. So you will notice that there are bonds that would require a large amount of energy to break it. Okay. Now we have here. So we have here oxygen bonded to another oxygen. To break that bond, it will require 34 kilocalories per mole. Okay? 34 kilocalories per mole. SS bond, or the disulfide bond, requires 51 kilocalories. Carbon to nitrogen, we have 70. Sulfur to hydrogen, or thiol, you have here 81. Carbon to carbon, 82. Carbon to oxygen, 84. Nitrogen to hydrogen, 94. Oxygen with a double bond, 96. Carbon to hydrogen, 99. Carbon with double bond to sulfur, 108. Your OH bond requires 110 kilocalories. Double bond between two carbons, 147. Similar to carbon double bonded to nitrogen, 147. And the strongest of these bonds here that are shown is your carbon to oxygen bond, requiring 164 kilocalories. Okay. So let us just say in the digestive process where enzymes has to cut these bonds. So this would be very easy to break, because that only requires 34 kilocalories compared to this one, which is 164 kilocalories. Did you get it? Okay. Because of these bonds, biomolecules fold to position polar and charged groups on their surfaces. So molecules fold to position polar and charged groups on their surfaces. So meaning to say that when a protein is synthesized, and proteins are made up of amino acids. So one amino acid is string to another amino acid, so that you will have a string of amino acids. But it does not stay that way, because the amino acids, there are amino acids that are negatively charged, there are those that are positively charged. And so what happens? You will have salt bonds. So most biomolecules are amphipathic. That is, they possess regions rich in charge, positive or negative, or polar, whether it is soluble in water or not. Okay? As well as regions with hydrophobic character. So there are portions of the protein that is hydrophobic, meaning they do not like water. So when you have hydrophobic compounds and you place it in water, this hydrophobic material will cling to each other. The reason for that is they do not want the water. So they cling to each other. So it's like the saying, it says, birds of the same feathers What is the rest of that? Birds of the same flock together.
Are chickens.
Oh, right.
Are chickens.
Birds of the same feathers are still birds. Joke lang, joke. So birds of the same feathers flock together. The same way, you have hydrophobic materials, you put it in water, hydrophobic materials do not like water. So as much as possible, they cling to each other. They hug each other so that no water molecule can be in between them. No? So that's it. Proteins tend to fold with the R groups of amino acid with hydrophobic side chains in the interior. So when the protein molecule fold itself, those that have hydrophobic area are put inside, while the surface area of that molecule, or yes, that protein molecule, are exposed to the water around it. Okay? All right. So we call that hydrophobic interactions. That is also what we call a non-covalent bond. Hydrophobic interaction. Okay. So hydrophobic interaction. Then we have electrostatic interactions. So these are due to charge groups. A positive to negative. One positively charged tail of an amino acid is attracted to the negative charge of another tail of an amino acid. And they form what we call salt bonds or salt bridges. Salt bridges are comparable in strength to hydrogen bonds, but they act over longer distances than the hydrogen bonds, oxygen to hydrogen. Okay? Van der Waals. Van der Waals forces arises from attractions between dipoles generated by rapid movement of electrons of all neutral atoms. It is significantly weaker than a hydrogen bond, but potentially extremely numerous. The Van der Waals decrease. Van der Waals forces decreases as the sixth power excuse me, of the distance separating atoms. Those, they act over very short distances, typically 2 to 4 angstrom. Now, Van der Waals, you can liken this to gravity. Okay? Without the gravitational force of our Earth, we fall into space. No? But we are held down because of that gravitational force. Now, molecules also exhibit a form of gravitational force. But this gravitational force is very, very weak. Okay? You can hardly detect it unless you have an instrument, a very sensitive instrument, to be able to measure this force. And this is named after van der Waals. Okay. Significantly very weak hydrogen bonds, but extremely numerous. However, as the distance increases from the molecules, from two molecules, the power now is diminished to attract each other. So they act over very short distances. Now, typically 2 to 4 angstrom. Okay. And you cannot even see 1 angstrom. No? Okay. So combining these forces, your covalent and your non-covalent bonding or attractions are utilized in forming the structure of biomolecules. While each individual DNA strand is held together by covalent bonds, the two strands of the helix are held together by non-covalent bonds such as hydrogen bonds. Following, of course, the Watson-Crick base pairing. You are, of course, familiar with that, no? Base pairing, C to G, G to C, A to T, T to A. Now, C to G meaning cytosine to guanine, and guanine to cytosine, adenine to thymine, and thymine to adenine. The force that is holding them is not so very weak. No? It's just like a hydrogen bond. Okay. Now, you can look at figure 34, that's chapter 34, no? That's 2. I think we have it here. Oh, wala din. So you just look at how it looks. 34-2. That is chapter 34, number 2 figure. Okay. Water is an excellent nucleophile. So what do you mean by nucleophile? And the other one is an electrophile. Wait a minute. My battery is running low. Okay. My battery is running low, so I have to put in the charger. So metabolic reactions often involve the attack by lone pairs of electrons residing on an electron-rich molecule termed nucleophiles upon an electron-poor atoms called electrophiles. So your nucleophile is electron-rich, while your electrophile very poor electrons, number of electrons. Nucleophiles and electrophiles do not necessarily possess a formal negative or positive charge. Water hosts two lone pairs of sp3 electrons bear a partial negative charge. You have seen that in the tetrahedron, and becomes an excellent nucleophile. Other nucleophiles of biologic importance include oxygen, atoms of the phosphates, alcohols, and carboxylic acids. The sulfur of thiols is its group, the nitrogen atom of amines, and of imidazole ring of histidine. Common electrophiles include carbonyl groups in amides, esters, aldehydes, ketones, and the phosphorus atom of phosphoesters. All right. Let's now look into water. Water molecules, although it is a very stable compound, it has the tendency to dissociate. However, its dissociation is very, very small. Okay? How small it is? It's just like this. You know, of course, in Tacloban is surrounded with water, diba? Now, you go to San Jose, you bring a bucket, an empty bucket, and you go to the water, to the sea, get a bucket of water. Now, you know that you remove one bucket of water, right? But the sea there, the ocean, does not seem to mind that you remove one bucket of water. But it is true that you got one bucket of water. So this is comparable now to what we call the dissociation of water. Although water can dissociate, its dissociation is very, very low. Very, very low. All right. You have seen here an equation right away, and some of you may have detest the presence of equation. Now, do not be do not be scared of this, because I'm not going to ask you on this. This is just only part of understanding what is meant by the dissociation of water. No?
So, Doc, we're not about to solve anything of these equations.
Well, there might be a little, but not, you know, just like in your math subjects.
Ay na lang, Doc.
Ha? Guti ay la.
Ay na lang, good.
Okay. So this is
Saan mo namon ni Doc?
dissociation of water here. And it's a constant. So the constant, the dissociation constant of water is the hydrogen ion concentration times the hydroxyl ion concentration divided by the concentration of water. So that's dissociation. As long as you can just be able to know what is that. If you are presented with an equation like this, diba? Mingon niya ka, kinsa unsa man na? Okay. pH, now this is whether the solution is negative, or I mean acidic, or the solution is alkaline or basic. Now, the pH is the negative logarithm of the hydrogen ion concentration. So this is it, pH, the negative log of hydrogen ion concentration. If you know this hydrogen ion concentration, you can solve for the pH. Now, however, at this point of time, we will not be measuring the pH, because when you are already in your clinical years, you will be asked for the pH of the plasma of your patient and how to correct that pH by the use of buffers. Okay? So the definition, while not rigorous, suffices for many biochemical purposes to calculate pH of the solution. All right. How to do that? 3 steps only. Calculate the hydrogen ion concentration, calculate the base 10 logarithm of your hydrogen ion concentration, and it is the negative value found in the second step. Okay, so all you have to know, of course, you know what is logarithm. You have passed this. Now, for example, pure water, mineral water. Why do you call it mineral? The one that is in bottles. Don't you know that there is no more mineral in that water? And still you call it mineral water? No? That mineral, that water has passed through several filters. The filter of all the minerals. So that's a misnomer calling it mineral water. There's no more mineral there. Okay? All right. So it says here, example, pure water. That's pure water. Rainwater drops from the sky, of course, in a polluted environment, that rainwater will catch the pollution. So once it goes down to you, that's already contaminated by the pollutants. But if there is no pollutants in the air or the atmosphere, that is considered as pure water. So, pure water at 25 degrees centigrade. Now, this is not the average temperature, room temperature. This is the room temperature in the United States. That's where the books came from. What is our normal room temperature? It is not 25. It's higher than that. Sometimes it reaches 32, 36, or even 40. No? So pH is negative log of hydrogen ion concentration. Pure water is the concentration of pure water is 1 times 10 to minus 7. So the negative log of 10 minus 7 is equals to negative 7, and you have pH 7, pure water. Okay? Okay. Let's go to acids and bases. Acids are proton donors. What do you mean by that? Very good. Protons, no? They're proton donors. What about bases? They are accept hydrogen or protons. Very good. Now, give me an example of an acid.
Ascorbic.
Oh, there you are. Oh, hydrochloric acid, sulfuric acid.
Sulfuric
No?
acid.
Acetic acid.
No?
Vitamin
Okay.
C.
So, I beg your pardon, it's not acid. Because once you have that in water, no, it contains potassium, and the potassium reacts with water, produces potassium hydroxide, and what happens now? It becomes alkaline. Diba? All right. Strong acid like sulfuric acid, hydrochloric acid, dissociate completely. What do you mean by that? Wala, nakalimutan na ang chemistry sa kindergarten. You learned that in your kindergarten, di ba? Meaning to say, example, you have hydrochloric acid, dissociate completely, meaning be separate the ions, the hydrogen ions, completely separate from chloride ions. So with sulfuric acid, because that's a strong acid, hydrogen ions separate completely from the sulfate ions. All right. Now, what do you mean by weak acids? They do not dissociate completely. Very good. No? All right. There might be a little amount of dissociation, just like your water. It's not complete dissociation. Okay. Now, strong acid, strong bases. Now, let's go back again to acids. When hydrochloric acid dissociate, you produce hydrogen ions and chloride ions. Okay. The chloride ions is the conjugate base. Conjugate. You know, it's the meaning of conjugate, no? When you have conjugal property, it's husband and wife property, di ba? Conjugal or conjugate. So, in the dissociation of hydrochloric acid, your chloride is your conjugate base. Okay, no? Now, as well in sulfuric acid, your sulfate is the conjugate base of sulfuric acid. Now, when we say or when we ask strong bases or a base. Your example right away is potassium hydroxide, sodium hydroxide, right? Actually, in the strict sense, in the strict sense, potassium hydroxide and sodium hydroxide, they are not called bases. They are called alkalis. They are called alkalis. A base is the one that I mentioned earlier. What is the conjugate base of hydrochloric acid? Chloride, diba? No. See, chloride is a base because the chloride can accept a proton. And what is a proton?
Hydrogen.
There you are. So it says bases are proton acceptors. Correct? Bases are proton acceptors. So if you say potassium hydroxide, can a potassium hydroxide accept a proton? What is the compound? Diba? Potassium hydroxide and sodium hydroxide, they have a basic component. And what is that basic component? That's hydroxyl. That's your OH. The OH there is the conjugate base. When? Because your hydroxyl can accept a hydrogen or a proton. So the OH accept a proton, it becomes water, correct? Huh? Or sodium hydroxide, yes.
Yes.
So they are alkaline, alkalis, no? Alkali. All right. So in the strict sense of the definition, bases are proton acceptors. We cannot accept potassium hydroxide as a base or a sodium hydroxide. But they have basic property. Why? Because these compounds, once they are in water, they dissociate into potassium and hydroxyl. And the water around it reacts with the hydroxyl to form molecules of water. And what about the potassium? The potassium takes the OH from the water to form potassium hydroxide. Correct? All right. So let's not debate on that. Potassium hydroxide and sodium hydroxide are just say they are bases, yes, because they have basic property because of the OH. Okay? All right. All right, so strong bases completely dissociate, just like strong acids. Weak bases, like weak acids, do not dissociate completely. Okay? All right. Here's just an example of your pH determination. Okay? You have your pH equals negative log of hydrogen ion concentration, and that is the negative log of 3.2 times 10 to the minus 4. No? 3.2 times 10 to the minus 4. Okay. So that is the hydrogen ion concentration. So the negative log of 3.2 is 0.5. And your multiplication here, the sign of multiplication, is changed to negative. Here, no? Multiplication, negative. Negative log 10 minus 4. And what is the log of 10 minus 4? It is the exponent itself. And the exponent is negative 4. No? And if you remove this, because that's negative, if you remove that, that becomes positive 4. Okay? So you have negative 5 plus 4 is 3.5. Diba? They have different signs, man. Diba? So you go into subtraction. You learn this in your math kindergarten. Did you pass for kindergarten? Joke lang. Water is pH. Water, what is, what is the pH? Of a solution whose hydroxide ion concentration is 4 times 10 to the minus 4 moles per liter. So when we say pH, that is the hydrogen ion concentration. The opposite of that would be pOH. That would be hydroxyl ion concentration. So the dissociation constant of water is equals to concentration of hydrogen ion times the concentration of hydroxyl ion equals 10 to minus 14. So pH plus pOH equals 14. How? If you can solve for the pH, then all you have to do is subtract it from 14 and you will get the pOH, or vice versa. You solve first for the pOH, and if you want the pH, you subtract pOH from 14 to give you the pH. No? So to solve this problem by, okay. To solve this problem by this approach, the hydroxyl ion concentration is 4 times 10 to the minus 4. No? All right. We first define quantity pOH that is equal to negative log of hydroxyl ions. And pOH equals negative. So pOH here equals negative log of hydroxyl ions. And what's the hydroxyl ions is 4 times 10 to the minus 4. Okay. So negative log of 4 times 10 to the minus 4 equals, log of 4 is 0.6. Log of 10 minus 4 is the exponent itself. And you change the sign, negative to positive. You remove that parenthesis there, you change the sign of 4 and becomes positive. So 0.6 minus a plus 4 equals 3.4 because that's negative there. Okay? If ever we have some problems like this, we will not give you a very hard problem. No? This is just only to understand what is. Because you will need this really when you go into your clinical, especially when your patient is acidotic or alkalotic, and you have to compute for the solution that you are going to give to your patient through the veins. Okay? All right. Anong duha naman balik naman Dili. All right. Wait a minute. Water is an excellent nucleophile. We have this already, di ba? Kanina? Or our slide jump off. Oh, well, anyway.
Yes, Doc, tapos na.
Tapos na, no? So
Yes,
it
Doc.
jump off. Oh, jump off to kanina. Just to be the last. Now, there's one there in the chapter, the Hasselbalch's equation. Now, that Hasselbalch's equation, you will have more of that. So, at the moment, we will not do something about it. No. You will do some calculations later on in your clinical years using the Hasselbalch's equation. Okay? All right, so this is it. Thank you for your attendance. Oh, by the way, are you all present? Huh? Siya?
Dok, may absent si Koan, si Chang Chang.
Balik sa Chang-Chang?
Oh,
Okay. All right. Now, why don't we introduce ourselves? Huh? Okay. You have seen my name, Fabito Monsanto. I graduated from Southwestern University. That was the first medical school in the Visayas. And I had my further study in UP College of Medicine for my biochemistry. I am a fellow of the Philippine Association of Academic Biochemists. I am married with 3 kids, and I have already some grandchildren and great-grandchildren. Okay. All right, let's start with anybody there. Just tell us. By the way, you tell us what was your preparatory course. You say whether you are medtech or nurse or whatever, and where you came from, and what school. Okay.
Sige, Dok, kay damo pa. Number 1, Aba, Razida.
Sige, come on, let's start. Anybody would like to start?